Thanks for the introduction and the invitation.
Keep talking.
Please don't spangle me. Thank you. It's a great pleasure to be here, and many thanks to the organizers for putting us together in this room, into this little bit remote place, so that we can have a lot of interaction among each other. I was asked recently, two weeks ago or so, if I wanted to give a tutorial about Magneto-Transport. I accidentally say yes, and I'm happy to let us say yes. And then I started working on this project, and then it turned out that I chose a working title, and this is kind of maybe fitting better to the scope of my talk. I will kind of what is surfing the wave and pumping the charge. So you will see a lot about inverse spin-Hall effect, spin pumping, and spin-Hall magnetoresistance. I also want to acknowledge the funding agency, the German Science Foundation, which supports this work via the Excellence Cluster of the Nanosystems Initiative Munich and the Priority Program of Spincurrents. So I want to blow in the same horn as you did, Thomas. I think it's important to look at the competitors. And I think the main competitor for spin electronics or antiferromagnetic electronics will be silicon. And they have maybe some head start, but I think it's not too desperate our situation, because silicon electronics only uses the charge degree of freedom for information processing. And I think the magnetism community provides already a pretty nice contribution in terms of magnetic data storage, and is working in the direction of non-volatile magnetic ramps. So I think it's interesting, and it has a lot of future to combine the spin degree of freedom with the charge degree of freedom, all these type of applications. And for this is the main theme of the talk, the interplay between charge and spin that play a major role. So what am I going to talk about? Pure Spincurrents, spin-Hall effect. How does that come about from an entirely experimental perspective? Then spin pumping, how to create spin currents, and then at the end of it, a bit of spin-Hall magnetoresistance to finish the talk. Okay, let's start with a basic introduction from an experimental perspective. And I think I was asked by 5 or 10 people in the audience why I can be here, as I'm a Bavarian and the Oktoberfest is running. Is that okay? I take on the theme and bring to you charge carriers, and there's a spin degree of freedom in the form of a dildo and a lederhosen, and so we will discuss a little bit transport in ordinary metals with dildo and lederhosen. So you have these, they have no long-range magnetic order. You have these kind of evidently represent spin, so lederhosen is spin down, spin up, dildo is spin down. And you have, hopefully, for the Oktoberfest, an equal population of lederhosen and dildo. And typically the show starts in this configuration. You want to get these guys moving. Here is the train station. Here is a potential minimum, and so there is some drive or a charge current if you fly electric fields towards this direction. If you have magnetic fields, then evidently you will think, okay, the charge degree of freedom matters, and the Lorentz force tells you that you have to move to the left with your charge carriers. And yes, this is true. The question is there a dildo and lederhosen analogon? And I have to think quite hard about it. And I want to show you this object, which you can actually find on many of these Oktoberfests or derivatives of the Oktoberfests. And that looks like this is a rotating barrel, and then you have to move through. And you see that there is some slight deflection and some additional resistance going on while moving through this tunnel. And the idea is that the deflection initially happens, but then you have a potential build-up or a charge carrier accumulation at one of the ends. this gives rise to a perpendicular electric field, and then you have again straight charge carrier motion. And you can measure this by measuring the electric field from here to here, and we will come a little bit later to it how this is actually done. You can also kind of inform yourself about the resistance by measuring the electric field in the longitudinal direction. You then have to parameterize this, and the typical way to do this is that you identify a Hall resistance kind of reacting on this charge current. The Hall resistance will depend on the external magnetic field, of course. And I want to kind of say here that you have to take a little bit care because this electric field in y direction is perpendicular on the charge current direction. You can do the same thing for the longitudinal direction, and then you have basically characterized the system. This technique is rather useful. You typically, well, all of you will know that you can measure the charge carrier concentration in that. So it's one of the standard techniques, not only for metals, but also for semiconductors. And it might also allow you to determine the type of charge carrier, if it's an electron or a hole. This is a particular case because it is an open boundary condition, so there is no charge current flow in the y direction here. And you always should have a quick moment of thought about this. Because from time to time you run into the problem that there is an open boundary or closed boundary. Here you control both sides, at least intellectually. And this kind of changes then your longitudinal resistance because in a simple speaking manner you have a kind of more diagonal motion of your charges and therefore along the pathway from here to here. Okay, and this is quadratic in the Hall angle, and so the point of why I want to make it is that there is some analogies in the spin Hall magnetoresistance. Okay, spin currents. So we had Dirndl and Lederhosen. The Lederhosen was spin up, the Dirndl was spin down. And there's not only kind of charge or people to be transported from the top left to the bottom right, but you can also do the opposite. So at some point, there might be more incentive for Lederhosen to go to the Löwenwald, while Dirndl kind of decides to move back, and then you can create a situation where you have no net charge current, but you have gender current. In some simple picture. And what you should take care of here, if you kind of communicate in charges, is that you kind of define this charge current spin up and spin down, and if you want to go to a spin current, then you have to renormalize to the electronic charge to get from a charge current to a particle flow current. And then you typically multiply by an h bar over 2 to address the fact that you are transporting spin or gender, depends. Okay, so up to now we haven't done anything. There is no interaction between the two. And Hyro this morning gave a beautiful introduction what can happen or what kind of options you have to let them interact with spin current and the charge current. So there's spin orbit coupling. There are various scattering mechanisms in metals, skew scattering, side jump scattering, or band structure arguments. Why a charge current direction can force a spin current in the orthogonal direction. And for me, experimentally, it's basically really this picture. Or in a phenomenological picture, that you have a charge current, you have an orthogonal spin current, and what we do, and this I think was the discussion between Axel and Hyro, is you want to kind of characterize it in a simple quantity, the spin Hall angle, and then there's all the debate, or there was a debate, is what is contained in the spin Hall angle and what is in microscopic orbit. And what should experimentalists claim or put as a number here, and how much modeling? Nevertheless, if you believe that this is just a number, then the prefactor already again looks familiar. You would want to convert the charge current into a flow, in a particle flow, and then you have your h bar over 2 to come to spin currents. You also need to take into the consideration that the quantization axis of the spin might matter. The quantization of the spin then gives you a direction of the spin current flow, so this cross product is of importance. You might ask yourself the question if there are the inverse process, and the simple answer, yes, there is. You can have a spin current, and then you source a charge current from this. And this is heavily relied on for many detection techniques which are interested in quantifying the spin current. Because at the end of the day, we are at least using electronics in the lab, and that means that we want to measure potential difference, charge flow, something electronically accessible. Okay. So again, there are boundary conditions involved in this process, similar to the Hall effect. And here you have just a spin accumulation then at the boundaries of your methods lab. Or in other words, you have a gradient of your spin chemical potential, which gives then a steady state balance for this process. And the question is, can you measure this? And I want to refer here to work from more than a decade ago by Hartmann and Aufstellung. So they use gallium arsenide. I think Harold showed this as well. A charge current is forced here into the top direction. You have spin up charge carriers accumulated at the left, spin down charge carriers accumulated to the right, and the question is, can you make them visible? And the experimentalist answer is yes, you can. Hartmann and Aufstellung did this by doing Coherent microscopy, or in other words, they measured the spin accumulation here at the edges of the gallium arsenide slab. And then you do some test experiments. You can invert the current direction, and you can then also crank up here an infinite magnetic field, and then this signature should be gone due to the fact that the spins start precessing. So the inverse spin Hall effect, I want to refer here to Valenzuela and Tinkham, starts with the question, how can I initially create a spin current? And then I convert it to a charge current, and the idea is here, so this is the top view of the device, this is a side view of the device. So the idea is that you have a spin current flowing by some source from the left to the right into this crossing section, which was in this case out of aluminium. Here we have a spin current. The inverse spin Hall effects converts the spin current into a charge current, and this is what you measure eventually. And the idea for getting a spin current to flow here is that you need a spin accumulation underneath this object, and this object is a ferromagnet, and you force the spin accumulation in there by having a current here. You should actually source the current in the opposite way to have here a pure spin. I checked this by applying magnetic fields. Magnetic field is important because you kind of align here the spin direction into the out-of-plane direction, and then you see this characteristica. They investigated this and convinced the audience that the aluminum has a small spin Hall angle, first of all, and that the spin flip length is actually reasonably long. This was then investigated for various materials, and I think still the most easy to handle material is platinum. It has a spin Hall angle of 0.11, 0.15, which makes it nice for detection, and it's nice for fabrication because you can just evaporate it in your deposition chambers rather easily. Okay, so there are also closed boundary conditions, or open and closed boundary conditions, and this is what leads eventually to the spin Hall magnetoresistance. And again, I just want to cut it a little bit short here. The trick is that similar to the ordinary Hall effect, you have basically a change in your resistance, which is roughly scaling with the square of this Gaussian Hall angle, and this is kind of what factors into it. So what should you take away from this first bit of the talk? You can have pure charge current, you can have pure spin current. It's a bit a matter of what property you're looking at, what kind of transport quantum you're transporting, and that there is an interplay or interconversion in the form of the inverse spin Hall effect or the spin Hall effect. Okay, so we entered this business some years ago in the direction of creating spin currents via spin pumping, and therefore I want to kind of guide you a bit through this project, and I think it's one of our projects where we really work with antiferromagnets, so do not want to miss the opportunity. Okay, for this is we are creating a spin current with coherent magnetization dynamics or ferromagnetic resonance, and then I want to go to spin pumping in damping detection and electric field detection. So, and the simple excursion for, or kind of shorthand intro for ferromagnetic resonance is the following. The magnetization measures, and your magnetization lives in a ferromagnetic film. And then the question ends up typically to be which is the orientation of the magnetization, and how does it depend on the external parameters. So what you do experimentally is you have an external magnetic field, that's H0, then you have shape anisotropy or demagnetization energies, which force your magnetization here into the plane. You have crystalline anisotropies or other anisotropies, exchange, and so on and so on. And you can cleverly kind of compile the whole bit into an effective magnetic field and say, okay, I'm aligning along this effective magnetic field. Then you shine in microwaves and drive this magnetization out of equilibrium, which is a process governed by the equation of motion, and the equation of motion is here the Landau difference equation. This is obviously not the whole truth, because you need to consider damping, and this is kind of handled by the second term here, that's the Gilbert damping term, which tries to force you back here into the equilibrium position. And then you might ask the questions, okay, that's all nice, but I want to have numbers because I have to design an experiment. And then you kind of plug in the numbers and plot your resonance frequency as function of the magnetic field, this dispersion-like curve, and then you see, okay, if I neglect any anisotropies, and account only for external magnetic fields, then I'm getting basically a straight line with a G factor of roughly 2, so that means 10 gigahertz is 10 gigahertz could be actually 0.3 delta, so there must be a factor of 2 primes. Okay, nevertheless, what else can you take into account? And there come the uniaxial anisotropies in. If you have uniaxial anisotropies, then the effective magnetic field is not necessarily in the direction of the external magnetic field, and this gives to a modification of the resonance as function of field curves. And then you can think about what you want to measure. You can either measure, or one of the typical arrangements is you measure fixed frequency as function of the orientation, and you should measure actually 2 polar angles here. Or you can measure as function of the magnetic field here in the high field range. This is typically done if you're more interested in the damping, because the Gilbert damping is coming out if you're looking at the line width as function of the resonance frequency. I want to introduce to you both methods quickly. So For a continuous wave of fixed frequency magnetic resonance, ferromagnetic resonance, you have a microwave source. You shine the microwave on a so-called microwave resonator or microwave cavity in this case. The microwave cavity has the advantage that there is a clear microwave standing wave building up in your cavity, which separates microwave magnetic fields from microwave electric fields, and so you can opt if you kind of put your sample more in the microwave drive region or in the electric field drive region, which can be of some importance or interest to you if you want to identify if you have an electric field drive or a magnetic field drive. The other advantage of this cavity type of approaches is that you can easily fiddle loom wires or electric contacts into the system to measure spin count. What you obtain as a signal is the high frequency susceptibility of the magnetization, which has an imaginary part which corresponds to an additional or a loss in the quality factor of your microwave resonator, or a real part which shifts the resonance frequency of your microwave resonator. You can measure both simultaneously or individually. Nevertheless, if you do it correctly, one of the quantities are sufficient to determine the resonance frequency and the line width. The alternative way that you can go is broadband FMR. And the idea is that you pack your sample here on a coplanar waveguide and look at the inductive response. The coplanar waveguide is derived from a coaxial cradle, as you might have it in your lab, or in your, at least in your mobile phone. And this is a planarized version of it, where you have the outer shield or the ground plane on the sides, and then the center line or signal line on the inside. And the trick is that you just put your sample on top of this. The center line is excited with a oscillating electric field, or AC, also AC current. This AC current makes an AC magnetic field, excites the magnetization precession in the sample. And then there's a back action onto your center line, purely inductively, as you would expect from Maxwell's equation. Typical examples look like this. You have to connect to the outer world. This is handled by this not so easy to see connectors. These are called end launch connectors, or here solder connectors that are soldered on, which allow you to kind of extract the microwave in a perpendicular geometry to this printed circuit board. If you're going for the broadband configuration, you have typically the advantage that you can enter superconducting solenoids. You have to take a little bit care because microwave cabling on this length scale of 2 meters and then orientation might be challenging depending on the accuracy that you need. And there's also another bit that you should invest in. It's called a magic device or a vector network analyzer, which provides you with the AC electromagnetic wave, kind of sends it here through and analyzes it in the fashion that you see the complex voltage ratio of the detector versus the emitter. If you follow this process, you measure signals like this for fixed frequency. You can do this now for various frequencies. You can follow the resonance curve. Here a permanent copper or permanent platinum example. You can extract the damping as function of frequency, and that is what I wanted to aim for with Hilbert damping. So you would expect that there's a linear relation between the line width of your magnetic resonance as function of the resonance frequency. And from this slope here, you get your Hilbert damping parameter alpha. You can also work this out quantitatively. If you measure S21 correctly, then you can trace back to the high frequency FMR susceptibility, given some impedance factors and a little bit geometry. Okay, how does that work for antiferromagnets? Helen gave a beautiful overview in how to do FMR with antiferromagnets yesterday, and we kind of tried this experimentally in the configuration where the external magnetic field is in line with the main axis of the antiferromagnet. And below the air temperature, the system orders like this. And the question is, where is the spin flop field? And the spin flop field is a balance where the Zeeman energy exceeds anisotropy and exchange energies. And the simple picture is that you apply magnetic field, nothing happens, and at the spin flop field, the systems change into this configuration. If you want to do dynamics, you have to carefully analyze now two sublattices, which are coupled via the exchange parameter. And this gives the massive boost in high frequency. And I want to jump here then basically to the prototypical example that we were looking at, which is magnesium difluoride. You can actually buy it. It's nice to handle. The problem is don't bring it in contact with water because it dissolves. That's the short message. We have learned this, and this is not so nice for fabrication technology, that I have to say. These are the typical parameters. You see I've stolen this picture or used this picture already, and it's transparent, so it's a antiferromagnetic insulator, which makes some things easier. Okay, we also learned from Helen that there might be a frequency issue for normal microwave technologies, because with zero magnetic field we're talking about 260 gigahertz. And since we didn't have the equipment, okay, we thought, we should go basically here. Below 30 gigahertz. Well, this was the borderline, and that this is actually true was demonstrated already 20 years ago by Hajiwara. And then you think, okay, interesting, there's only a point here at maybe 50 gigahertz, and then there are here points, so you want to be get a bit, worried about, is the blue line really hitting the zero or not? And we have had this picture also several times already up yesterday, and this kind of shows you the magnetization function of the externally applied magnetic field. And you notice that there is basically zero field with a orientation of the z-axis in parallel to the external magnetic field. Zero, there is this kind of discrete jump. If you go slightly off, then the system is getting washed out, and so we got then really worried because you have to align pretty well. And keep in mind, the dipsticks are roughly 2 meters long, and you have a 2-year-old piece at the bottom, and you want to align it with better than maybe 5 degrees with the main axis of Z parallel to your axis. We calculated this. You see there's this high frequency branch, a low frequency branch, and if you do the numerics, you notice that 25 gigahertz means you should be better than 5 degrees aligned. And this made the undertaking experimentally challenged. Nevertheless, we managed it to 2.02 degrees, so you can kind of figure later on out if you see a resonance misalignment. I have to say that this was kind of achieved only by multiple cool-downs and adjusting the kind of bit piece bit by bit and kind of guessing which mistilt you have. Okay. So this is one way of exciting coherent dynamics by microwaves in ferromagnets or antiferromagnets. And then the question is, can utilize it for something. And this was suggested also 15 years ago, almost, by Zerkovniak and co-workers, naming the process of spin pumping. So you have here an excitation of your magnetic system, and you have the intrinsic damping, which is kind of indicated in blue. And if you pack a normal metal on top, then you have here something which I would now call an open boundary condition, so you can source a spin current into your normal metal. And this will evidently lead to a damping here in the spin system, because you need to drive the spin current here. Additionally, you can then use the inverse spin Hall effect to measure this voltage also electrically. This whole process is called spin pumping. It was coined that this is a damping-like term with spin mixing conductance. And what I said is that you expect for your ferromagnet an additional damping. The additional damping has also something to do with the thickness of the ferromagnet, or you can measure a DC spin current by looking at induced voltage or induced current in the normal metal. Yeah. So the additional damping, if you have access to broadband ferromagnetic resonance, this is reasonably straightforward. I showed you data already, so you measure constant frequency, the line width. You notice we have now gold and alloy. It has a weaker slope than platinum on thermaloid, or platinum on thermaloid has a higher damping. If you subtract the two Gilbert damping parameters that you have measured here, you get the spin pumping contribution of the damping, and from that you can get out basically the spin mixing parameters. What else can you do? You can measure DC current or DC voltage. The simple idea is you excite now the ferromagnet. You have spins injected in your normal metal. You have the inverse spin Hall effect. Then you kind of just have to pick up here this voltage. And there is where this nanovoltmeter comes in. The kind of preliminary work for this, or kind of seminal work, was done in the Axel Hoffmann's group. They did broadband ferromagnetic resonance. We decided here for cavity-based because it's easier to separate the oscillating electric field and the magnetic fields here. And so the only thing is, sample fabrication-wise, is that you come up with a sample. You just kind of connect two bond wires here, and then you measure the voltage. That's the short story. You then want to convince yourself that it's really the inverse spin Hall effect. And for this, you want to measure ferromagnetic resonance, the induced DC voltage. Here, if the DC voltage turns upwards, I want to quickly mention here that this bimodal signature is just due to measurement. We do here magnetic field modulation. So we learned already that the charge current, or the induced voltage, is related to the cross product to the spin current and the spin direction. So if you invert the external magnetic field, you invert the spin direction, and therefore you will expect to see here the same signature, but with a negative sign, which is actually here the case. And I also want to encourage the student to do some test experiments. If you go in the outer plane direction with the external magnetic field, then the spin current direction and the quantization direction of the spin should be in parallel, and you should expect no voltage, and this is roughly the case here. Okay. This is example for nickel and platinum. There was evidently then a rush what we could kind of investigate here. I don't want to go through this slide in detail, but magnetite, cobalt, phosphorus, dilute magnetic semiconductors like gallium manganese arsenide. They're also similar spin mixing conductances, which was actually promising use of that kind of time. You might wonder, what about the antiferromagnetic resonance? We managed to fabricate platinum on this manganese difluoride spike sample. So this is again the ferromagnetic resonance, or antiferromagnetic resonance in this case, and this is the corresponding detected voltage. And I kind of picked on, you want to see a sign inversion for negative fields to positive fields. This is not really evident here. We think that at this point, one contribution is maybe thermal heating or so leading to this induced voltage. But if you subtract this data set from this data set, so positive from negative field, to figure out the difference, and you notice that there is some remainder of signal which we attribute, or which is an indication for spin pumping from an antiferromagnet into the platinum strip. So this is how far we got in this project, and with this I want to switch a little bit gears to the actual topic of my talk, magneto-transport, and talk a bit about magneto-resistance, or spin Hall magneto-resistance. What did we do for this? We opted to the workhorse ferrimagnet. It's a ferrimagnetic insulator, yttrium iron garnet, and we placed platinum on top. The real neat thing of yttrium iron garnet is that you can't inject charge carriers. You can only inject spins, if you can. Again, we have the configuration of the spin Hall effect. We have a charge current sourced through this platinum strip. This accumulates here at the interface, in this example, as spins pointing to the right-hand side. And then the question is about what happens next. Pyro kind of introduced us to torques, to field-like torques, to damping-like torques, and so we understand this presently in terms of the spin transfer torque. So if you can manage to transfer a torque from this spin accumulation here to this magnetization, then you can identify this with an open boundary condition at this interface for the spin current. So you source the spin current into this magnetic material. If you are able to source the spin current, you have an enhanced dissipation rate, and this affects the resistance of the platinum layer. The good thing is that you can control the magnetization direction of yttrium iron garnet by an external magnetic field, because it's a ferrimagnet, and then you can play around with it. You can switch this to a configuration where S is parallel to M, then the torque vanishes, and then you would expect now a reduced dissipation rate in platinum. You can figure out the entire angular dependence that you expect here, which is basically this cosine square dependence that you have here. And with this, I also want to spend a few minutes on measuring resistance. So resistance is voltage divided by current. Typically, we have metal films of low resistance, so we have to take into account, or account for the fact that the leads from the actual device to the equipment measuring the resistance has some finite resistance, so there might be an influence by the leads. The trick is to go to a 4-wire method, because then the current is closed circuit. You can measure the current outside. If you kind of have here a voltage probe, then you measure the voltage drop, and then you can measure the real resistance. You can also improve on this by using switching methods. So you kind of ramp your current in for one side in this direction, then you invert the current and ramp the current in the other direction, and record the voltage for both directions. That's here called V plus and V minus. And the neat thing is that you can either subtract them from each other. That gives rise to all the odd terms of the current. If you add them, then you have all even terms in the current, and that is one of the techniques where you can determine or kind of distinguish between thermal effects and real resistive effects. This is kind of commonly known as sticky switching. You can have an even more fancy version of this, which is called a lock-in amplifier, which modulates the sign in a sinusoidal fashion for you. Be aware that if you use a lock-in amplifier, that you want not to overmodulate or modulate too quickly, because then the inductances of your circuit will matter, and this will kind of spoil your results if you're really interested in the DC resistance. To convince you that this actually works, we had spin current in the Z direction, charge current along here the X direction, and their corresponding these spins are aligned in the Y direction or along the T direction. So if we have our magnetization oriented along the J direction, or the external magnetic field along the J direction, we have a finite angle between the magnetization and the S direction, so high current or high resistance. If we align the magnetization along the T direction, then the cross product vanishes, the torque vanishes, and we have low resistance. And this is this cosine square that I promised you. You can do this in all three rotational planes. Here we have again the option of being in line with S, then you have low resistance, perpendicular to S, then you have high resistance, and here you're constantly rotating in a plane which is perpendicular to S, so you expect a constant high value which is given. You can then dig more into theory and analyze quantitatively this signal amplitude here. This is delta rho over rho, or delta R over R, which is a 10⁻⁴ effect. And from this, you can expect the spin-Hall angle, or better the product out of the spin-Hall angle and the spin diffusion length, as well as the spin diffusion length, if you go through the plane and measure as function of the film thickness. That means that you need a lot of samples to convince yourself that you can disentangle the lambda and the spin-Hall. And the actual neat thing is that Huebl group did this in the meanwhile, and we roughly agree on that. Okay, with this, I want to say a big thank you to all of the people who joined the road, who took part in this journey from the experimental side, this side, as well as from the theory side. And just want to kind of bring up my summary slide. I hope that you kind of got the experimentalists, the variant experimentalists' understanding of the spin-Hall effect, of spin-Hall physics, a little bit spin pumping, and spin-Hall resistance. Thanks a lot for your attention.
Questions? So I have a question. You have discussed in the microwave pumping experiments how to use DC, how to measure DC current. But I have seen on your slides that you mentioned AC current. Can you comment this point?
There is AC current, and I think it's...
Can you measure the signal when you AC signal when you pump spin current from a ferromagnetic, non-magnetic or antiferromagnetic material?
The simple answer is yes, you can, but it's tricky because you want to convince yourself that you have no spurious crosstalks, or that you are not able to, that you're not picking up your microwaves, because if you do the experiment, then the tricky bit is that you might have residual electric fields close to your device, because you have a high frequency magnetic field and a high frequency electric field. And the question is how to disentangle those and to convince really yourself that what you're measuring is high frequency spin pumping or AC spin pumping as it's called. And this makes DC spin pumping much, much easier. And there was a decent debate in literature of how to do it correctly.
Thank you. Please.
I just have a small question. Could you please go back to the different materials? I don't remember the slide
what?
number. So you had a slide called different materials.
Yeah.
So I'm sorry.
No. This one.
Yeah, here.
Yeah.
So here I understand that when you switch the direction of the magnetization, so due to the first protocol speed polarization and field, so you would get a voltage signal in the opposite direction.
Yeah.
But I just can't imagine how would you get like kind of behavior in O, in figure O. So like there's two ones.
Here, this one.
Yeah.
Yeah. So this, I really rushed through the slide. So this is, so you measure simultaneously the ferromagnetic resonance or the high frequency susceptibility of the ferromagnetic resonance, which is the top row here. So this is the ferromagnetic resonance signal for both field directions, and you are not expecting an inversion in the excitation of your ferromagnetic resonance itself. So this is high frequency, and this is the DC voltage that you pick up over your device. Corresponding to this nickel platinum. So this is all magnetic film plus platinum, nickel platinum, and this is the DC voltage that you obtain. And here you see the clear sign inversion.
Yeah,
And again,
this makes perfect sense. But I'm just wondering, figure O, there is two bumps.
say again.
So figure O, so you see there are two bumps.
There are two bumps, yeah?
Yeah, so I can't imagine how that works.
Okay, so this is a dilute magnetic semiconductor. And the dilute magnetic semiconductor, so this is in this particular case gallium arsenide. We see two resonances, two ferromagnetic resonances due to the fact that you can excite spin waves in the system, not with only the fundamental mode, but higher lying modes in the magnetic semiconductor. So how you should read the data is that you see this bimodal shape, and the resonance is actually here due to detection techniques. So you do a magnetic field modulation of the system, of the signal, and therefore you get the derivative of the high frequency response. So this is the resonance point, and therefore you have here a resonance point and here a resonance point. And this corresponds to this peak and that peak. So you see basically two resonances which are a little bit superimposed in this signature. So at the end of the day, this also tells you that for spin pumping, if you are pumping into a spin wave mode, you can also do the same trick and rectify it. Or you can use spin pumping to inverse spin Hall effect to do it.
More question? Yeah, please, Peter.
So the spin Hall magneto resistance is due to the direct inverse spin Hall effect, so it's proportional to spin Hall equals squared. Does that put a serious limit as how big the effect can be, and can you maybe comment on how that can be overcome?
The effect is small, evidently, and in particular because it's the angle squared, but I don't think there's any reasonable chance to overcome it in this sense. So you can opt for metals with a higher spin Hall angle, but I think there is also a natural limit. You can go to bismuth or tantalum-based materials which have 4.3, but you're entirely right that they are squared. And the question is that the fundamental question that I think that you are asking is how much. So let's go back to the particle picture. You have a charge that moves, and the question is how much spins can you move for this into the orthogonal direction? And I think this is a question that I would like to hope that are better answered by my theorist colleagues. If there are some tricks of reutilizing charge motion for spin current motion, like Hyrosec, so there was the discussion in the end, if you can have multiple scattering effects also enhance this. Do you want to comment?
Yeah, please.
No, I don't, but I have another good question. So you showed your very tedious experiment of the AFMR in manganese fluoride.
That's
That was
right.
one part of the curve, how tedious that experiment was, but you compared it with the measurement that was done 20 years ago showing the complete picture. What did you say? So it looks like it's a very difficult experiment to do, but then 20 years ago these people were able to measure the entire...
So there are two options. The old techniques relied on Russian technologies of the Russians developed some 20 years ago techniques for multiplying or a higher harmonic generation of microwaves. So you start with a microwave generator of decent amplitude, and then you generate higher harmonics. You filter out these higher harmonics, and then you can try to select or post-select the data in a transmission microwave, quasi-optical transmission experiment, and try to reconstruct the ferromagnetic resonance response.
So it's a very unique AFMR setup.
Yeah.
Only in Russia.
No, you can. Actually, most of the people that I yeah, but it's
name, I should say.
I said Russian technology. You see that everything happens in bands, and so there is a kind of dense point density here, where you can measure, and then you basically switch the apparatus, and you can measure here.
Right.
Then you have here a band, and here it's getting more and more convenient. But as far as I recall, this was microwave transmission.
I can comment that this manganese fluoride, it was really studied well in Soviet Union, but usually they used, in Ukraine also, they used optic technique, and they can even visualize 180 degree domain. But it was a very complicated technique because they excited the ions, different ions in different sublattices.
Yeah, but keep in mind, so if you're talking about 300 gigahertz, this is all quasi-optics in microwave electronics. And if you want to have smaller samples, then you have typically plastic lenses focusing this on the actual bulk sample, and so on and so on.
Okay, thank you.